Maybe we'll start at 7:05.
Yep. Okay, and we're live.
Yeah, you posted YouTube also.
Yep.
Okay, that's good. We'll wait another 3 minutes.
Sure, yeah. So at the end, if I understand it, I don't have to go to the Q&A myself.
Yeah, actually, what we'll do, myself, I'll review the Q&A, then I'll see appropriate questions to you.
Okay.
If you're able to answer a few questions by ourselves, some questions would be a general, some questions could be a technical,
Yeah.
which is need to be addressed.
Okay.
If the Q&A will be more, then we'll take it up via mail, or that will also will inform to all the participants.
Sure.
Yeah. Hope you at the end of the presentation you can give your mail ID so that people can approach you directly.
It's in the end of the presentation.
Yeah, that's good. So the photo is good, the screenshot for your first slide. It's from here.
Yes. Yeah. I'm not very good with PowerPoint, but I try to experiment a little bit.
Good.
The rest is substance. They are not so fancy.
Yeah, it's okay, but for structurally fancy.
Yeah.
I think now traffic is more, maybe people are on the way. Maybe they are on YouTube, maybe.
Now, yes, by the time we finish, traffic will be over.
Yeah. Generally, we used to conduct at 7:30 in AUD.
Yeah. Yes, I came once.
Okay.
Once it was about the development, one big development in London. I forget the name of the development. It was recent.
AUD here, the American Institute of Dubai. In Dubai,
Yeah.
okay, the project you mentioned.
Yes. Yeah.
Okay. Yeah, I think you can start now. Yeah. Good evening. Welcome to all of you on behalf of Institute of Structural Engineers, ISTRUCT. Today's CPT topic is fluid viscous damping, uses, benefits, and methods of implementation. And our speaker today is Mr. Nikos Tantlis. Just to brief about our system, you can see all the attendees at the bottom of the page. You have a Q&A session. You can post any questions, and at the end of the session, the question will be answered. We have a YouTube channel parallelly. You can see it via streaming. And one more answer is we have a PPT presentation available at the end. Will be shared with all attendees if contact is provided. That's about system. Just to brief about our speaker, he is a very well-experienced professional in structural engineering. He started career in Cyprus. He did his graduation from and post-graduation from Northwest University in the US. And he's got about 20+ years experience in locally. Out of which 15 years he worked at Wade Adams, which is the biggest company in infrastructure, and is currently a technical director, Foster International, which represents Taylor Devices in Middle East. And hope everybody will enjoy our talk today. Platform is yours, Mr. Nikos. Please proceed.
Thank you, Mr. Sama, for the introduction, and my thanks again to the regional chapter of the Institute of Structural Engineers for organizing this event. Good evening to all of you. For the next 1 hour, I will be talking to you and hopefully interacting with you on a very interesting subject that was actually, the technology was born about 100 years ago, but it matured into the civil engineering sector only in the last 30. The name of the technology is fluid orificing, and then devices that use this technology are called fluid viscous dampers. So without further ado, we'll proceed with our discussion. This is just to give you an idea of how this presentation is going to be organized. Initially, I'm going to use visual aids to show what a fluid viscous damper looks like and how it integrates within a civil engineering structure with emphasis to buildings. So we will be seeing cutouts, photos, and implementation examples. In the next group of slides, we will discuss the fundamental question, which is why use them? We have perfectly fine methods of designing buildings nowadays and bridges. So the question arises, why use a fluid viscous dampers? And then we will discuss the crux of the matter, which is how to analyze structures with dampers, how to preliminarily estimate their properties, and how to model them within the structure, what methods of analysis are amenable to dampers, and generally describe the process. Then we'll talk a little bit about specified dampers, how dampers are specified on a project generally, and then we will see some case studies. Just before we start, just to tell you a little bit about Taylor Devices. Taylor Devices is one of the pioneers of shock control and vibration in the world. They are based in the United States, in Buffalo, New York, and they were founded in 1955. And they are basically organized along 3 verticals, which is aerospace defense, industrial, and structural engineering. So the technology that we'll be discussing today has its origins in the aerospace and defense industry. So first we'll see how dampers will work. And to make this abundantly clear, we are going to go a little bit in a somewhat convoluted path. First, we'll see photos. What are fluid viscous dampers and how they work within a structural system. So we start, I mean, like they say, a picture is worth 1,000 words. So this is a picture. This is what a fluid viscous damper looks like. It's basically a piston, a shock absorber, and it's connected on the structure on two ends. It's a linear device which takes advantage of relative movement between the two ends that it's connected to. And this, now we are going into more detail. This is a cutout of a typical damper. As you can see, this is, there is a piston. There is a piston head assembly, which is perforated in a way with, I mean, it has orifices. And basically, through the movement of the piston, which is driven by the relative deformation of the two structural points to which the damper is connected, displaces fluid from one chamber to another. What this achieves is basically to generate a damping force. I mean, you all remember probably your single degree of freedom, dynamics model. I mean, it generates a damping force on which we will expand later. It's worth to note that, I mean, okay, here we show a typical Clevis connection. There are other types of connections as well, which can take advantage, I mean, take care of irregularities in the connection or sort of tolerance issues. I want you to know this green color thing, which is a cap and seal. This is a typical damper. The next one I'll show you is not typical, and I'll explain why. This on a typical damper, these caps and seals are usually structural polymers, if you are talking about a good quality damper. And Taylor Devices has patented structural polymers, which are used in fluid viscous dampers. On this type of damper, the maximum force that can be generated is about 9,000 kilonewtons, and the maximum stroke is 1 meter. Like I said before, we spoke about a typical damper. This is a non-typical damper, and it's worth examining for a few seconds. You remember the polymer seal in the damper. This damper is called a metal bellows damper, and it uses something called a metal bellows seal. The function is the same, is identical as the previous damper, basically fluid dissipating energy through heat by moving between compartments through orifices. But the important thing here to note is the metal bellows seal. This is very thin metal creating like an accordion structure. So this obviates, this makes the use of polymers or elastomers unnecessary. This damper does not contain any synthetic elements. It's just metal. And it was designed in that way to be used. I mean, it was initially conceived for space applications, but now it's used for wind applications, because in wind applications, we have many low amplitude cycles, which create the need for reliability. I mean, a structure will go through billions of cycles of wind vibrations in its lifetime. And this necessitates a system with reliability. Fluid metal bellows dampers are basically designed for infinite life. They are guaranteed for many years, 40 to 50 years, I mean, they are warranted, and they are designed to basically last as long as the structure. But the maximum force here is limited to 2,500 kilonewtons and the stroke to 0.5 meter. Now I'll show you a video which makes what I described before clearer. You'll see the damper in operation. The movement you see comes from the structure. It's basically relative movement between two ends. Let's say between the top of a story and the bottom of a story, as you will see later. Okay. Now, before we go further, we should describe what is a constitutive relationship for a damper. How does it work? I mean, we know visually how it works, but what parameters make it work? So the basic constitutive relationship in simple terms for a damper is what you see here in the left. The damper generates a damping force. This force is equal to a damping constant called C, which is characteristic of the damper. A damper is designed to have a specific C, a specific damping constant. And also it's proportional to the velocity of the motion, which we'll see later, I mean, how it relates to the movement of the structure. It's basically the relative velocity between two ends raised to an exponent A, alpha. Alpha can be set to any value from, I mean, 0.3 to 2, but usually, and this is something that we select from the beginning. I mean, this is also built into the damper through the damper's design, but it's something that we select during the preliminary stage, and we select on the basis of experience, basically, and certain special characteristics of the application. For example, when we have a wind dominant application, we usually use linear dampers or near linear, i.e. the alpha varies from 0.7 to 1. And the reason is to basically to make the dissipation of energy, controlled dissipation of energy, have lower forces at lower amplitudes in order to limit the power generation in the damper and basically avoid excessive energy dissipation. For earthquake applications, the exponent is lower. It could be 0.3 to 0.5 or to 0.6. And the reason being, as we also see later, the lower the exponent, the more efficient the damper is. I mean, for a given velocity, it dissipates more energy. And this is the last video I promised, just to show you. This is a comparison of two identical structures, one with dampers and one without, and you will see the difference in response visually. Now we're going to how to arrange dampers in structures. This is a schematic that shows typical story arrangements. There are other types of arrangements which we will see later, but these are arrangements typically installed on bay frames and take advantage of the differential movement of the interstory drift, basically. One recent development is the open space application. Sorry, this is the toggle application. The toggle application has the benefit of being able to amplify movement. Basically, this kind of application multiplies the movement in the damper 3 times in relation to the differential displacement, the interstory drift. This is the open space. It's a new development which allows basically to use the damper in horizontal position, but without obstructing space. The one to the left is a double diagonal arrangement. And this also has a different magnification factor. We'll see later. Basically, the movement in the damper here will be the interstory drift times cosine of the angle theta of the incline of the damper. This is called the chevron arrangement. Here to the right, where the gentleman is standing precariously, is the chevron arrangement, and this has a magnification factor of 1, i.e. the movement in the damper is the same movement as in the interstory drift. And this is a classical diagonal arrangement. This is another application. This is sometimes dampers are used in conjunction with base isolation in addition to lengthening the period of the building with the base isolators, to also impart substantial amounts of damping. This is used in highly seismic areas like in California or Latin America. This is called the mega brace configuration. If you look at the schematic in the left, the rendering, basically this is a configuration whereby the dampers are placed along a long external brace. We'll see a case study later where the brace, there is a brace that traverses 20 floors and basically makes up the lateral system of the building. The advantage of that is being able to collect movement over multiple floors and thereby optimize the behavior of the damper. This system has been used in a few very notable applications, like the 181 Fremont Street in San Francisco, California, which we will examine later, and the Torre Mayor building in Mexico. And I think the most important configuration for our area, where we have basically wind dominant applications in high-rise buildings, is the damped outrigger. The outrigger system is a well-known system to structural engineers, and is basically, it consists of connecting the core, as you very well know, to the perimeter frame through a stiff member or a system of stiff members to transfer moment, to convert moment into compression, to avoid dishing and to reduce the moment of the core. Here, what we do is we decouple the outrigger from the column. It's no longer a stiff arrangement, it's just a lever arm, which transfers basically relative movement between the core and the perimeter into the damper. And it's ideal for high-rise buildings who have mechanical floors and where you can have these arms like you have an outrigger, it's not really an outrigger, to operate in that way. Typical applications of that is 250 West 55th New York, 40-story building, which you will see later, and the San Francisco Shangri-La in the Philippines. This is a close-up, a better representation of the damped outrigger. You see the core here. You see the outriggers, and you see the outrigger to column damped connection. And this is what the actual connection looks like. On the left, you have a perimeter column. On the right, this is the edge of your outrigger, which is outrigger quote unquote. It doesn't work as an outrigger, it's just a lever arm. And in the middle, you have the damper, which is connected to both members. You see here is the typical bracketed connection. So now we have to see why you use fluid viscous dampers. So the fundamental questions to answer in this this discussion is, two fundamental questions. Why do we need supplementary damping? Because this is what dampers give us. And if we need supplementary damping, why use fluid viscous dampers in particular? So we will attempt to answer these questions. Just a few central ideas that are going to be pervasive through this discussion is basically work, to have a damper being a useful addition, a useful tool to our arsenal, we have to have two things. We have to have dynamic response, because this is how a damper works. And we have to find points who have substantial, when I say substantial, depends on the application. For wind, it could be 5, 10 millimeters. A substantial relative movement, which we can connect the damper to those 2 points, and we can have the damper operating efficiently. And obviously, we'll reinforce the idea, which I'm sure all of you know, that when we have to deal with the dynamic response, we have 2 options. We can either stiffen the structure or dampen the structure. And the dampers can be used in both for SLS, drift acceleration, or to reduce strength demands. But we can optimize for one. It will help the other as well, but the optimization has to be on one of the 2 categories. So this schematic just puts a perspective on what we said before. We have a building and we have some transient input, wind, earthquake, and dynamic influence. What happens to the building? A building basically accumulates potential, takes up kinetic energy or potential energy from an outside source. So what happens to this potential energy? It can happen, I mean, 3 things can happen. It can either become strain energy or kinetic energy, which means acceleration, drift, and stress and strain. It can become damage, plastic deformation, hysteresis, or it can be converted to heat through damping. And damping we have many, I mean, damping formally is divided into different categories. But for the purpose of this discussion, we have inherent damping, which is the damping that the structure possesses, whether you want to call it viscous or modal or whatever else. And you have supplemental damping that you give to the structure through a system. And this system, the system that we are discussing today, is fluid viscous dampers. Okay, so since we have 2 major sources of dynamic input, of course, we have others as well. We have blast, we have many others. But the 2 major ones is earthquake and wind. So I thought to answer the question of why we need damping through these particular categories. And in the first picture here, we see a typical family of response spectra for earthquake. And these response spectra are obviously not smoothed out design spectra. They are spectra generated by a specific ground motion. But you can see the obvious, which is basically stated in codes as well. I mean, in the ASC code chapter 18, where you have response reduction factors. And the fact is that you have, with damping, you reduce the spectral responses of the structure. You will see here that, for example, at a period of 0.5 seconds with 5% damping, you have almost an acceleration of 1.2 g. And if we go down this curve, when you are at 0.5, when you have 40% damping, your spectral acceleration has dropped to 0.4 g. So this behavior talks in itself. It's basically damping reduces dynamic response. That's why fluid viscous dampers are ideal for seismic retrofit. I mean, when you have basically structures that have to comply to more stringent earthquake criteria, you can use fluid viscous dampers. A typical addition in earthquake applications, the typical addition of damping is between 20 to 30%. Also, although I've seen studies that advocate up to 45%. This is a specific case. I mean, I wouldn't classify it as a case study. It is a case study, and I'm going to use it to reinforce the idea of that damping works. This is basically research done at Oxford University, and it involves the design of 3 buildings, concentric brace frame buildings, 4, 8, and 16 stories. And the buildings were designed to the Euro code in 3 ways. One way was to using the 0.5% drift criterion at SLS, 0.5% drift criterion at ULS, and then using fluid viscous dampers. And these are the results. What you see to the left is fragility curves, which basically describe the expected loss under the design earthquake. And you can see that basically for all the buildings, the building that was retrofitted with dampers, which is shown in red in both instances. In the top graphs, the blue is standard drift design, 0.5% at SLS, and in the bottom for the 16, sorry, this is at ULS, and in the bottom, the 16-story building is for SLS at ULS. So basically, the cost, the expected cost was calculated using FEMA P58, which is a method that allows the designer to assess the damage under a given earthquake. Basically, the cost of the structure with dampers to be repaired under a given earthquake will at ULS, at SLS will be the same cost. At UL, the damped structure at ULS will sustain damage equal to the damage that the undamped structure will sustain at SLS. To the right, this is shown in more detail. You see, for example, here, when we, on the 8-story building, when we have the damped structure will have basically 0 structural damage as opposed to the undamped structure. This is continuing. To the left, you see acceleration, to the top, the acceleration and drift for the 16-story building. Again, you see that the structure that is not equipped with dampers is performing much, the blue one is the one without dampers, is performing much worse. I mean, the acceleration at a given story is like more than double the acceleration for the damped structure. And the same is valid for drift. And I mean, just to give you an idea in terms of cost, the cost of this, I mean, equal the cost of the damper retrofit compared to the standard design, it was like 57% of the standard design in terms of material consumption. The 16-story building could not be designed to meet the stringent drift criterion, 0.5% at ULS. In the bottom, you see basically how the expected cost, the vertical axis is basically damped cost divided by undamped cost. And you see that as we increase the damping ratio, basically this number tends to 0.5 to 0.6 for the mean, which means basically the expected cost for repairs will be half. But if we look at the corollary, if we allow for the same deflection, same drift, same behavior, that means that you can reduce the stiffness of the building and have the same identical behavior as a building that is undamped. Now going to wind, this is a general principle. We know that for broadband processes like wind, the response of the building, the dynamic response of the building, any response, acceleration, moment, whatever, is something constant, is inversely proportional to the square root of damping. Okay, so what you see, the equations to the right express this fact basically for a crosswind vortex shedding. Basically, we expect all of the response to be dynamic. Therefore, this is how it's described. But for a long wind, we have a percentage of the response that is expected to be dynamic, and this is what is expressed here. What we see here on the graph is that, for example, if we have a purely dynamic response, I mean, for example, in vortex shedding, and we compare the response at 1% inherent damping versus 5% after we have used supplementary damping, the reduction in response will be about 50%. So your base moment, your acceleration, the dynamic response will be 50%. The top curve shows how this response will change if you have an event that has a dynamic content of about 20%. Let's say you have a long wind excitation and 20% is dynamic. You will see that with 6-7% damping, you will reduce your response by 20%. This is an actual curve. This is an actual set of damping curves from a project, and it shows the variation of base moment with damping. This is the moment along the x-axis with a wind of 30 meters per second, and you see that in the critical direction here and here, the base moment reduces by 50% when we add basically, I cannot see the legend to the right, 5% damping. When we add 5% damping, we reduce the response by 50% as compared to 1% of inherent damping. That's another schematic just to drive the point home. This is regarding damping and dynamic response in wind. Basically, as you can see here, once we have a given shape and size, the 3D form of the building, which also determines how the dynamic behavior, obviously, we have basically decided and determined the aerodynamic load. Once we have this aerodynamic load, the question is how will the structure respond to the aerodynamic load? And as you can see here, the things that will influence the dynamic response is stiffness and damping. I mean, with increasing damping, we reduce the dynamic response. With increasing stiffness, we basically again reduce the dynamic response by increasing the fundamental frequency. I saw this I was asked a question, when is it inevitable to use damping? And the answer is, you can always add stiffness, but stiffness means money. It means interfering with the elegance. And it also, as you can see, the response reduction is not as sensitive to stiffness as it is to damping. I mean, and this shows you that it's a more efficient way of taking care of dynamic response. So in summary, now we talk why we need damping. So let's see why we need fluid viscous dampers to give us this damping. They have several advantages. Basically, okay, that was the basis of our discussion so far. It enables slender structures by dissipating energy in a predictable manner. The fact that it's a distributed system, as you have seen, it's not one thing. You have a number of dampers distributed in the structure, creates redundancy. This allows the engineer to benefit from reductions in strength demand. So use it at ULS, not only to reduce acceleration or drift. They are, they are easy to install. Connections are straightforward. They are codified. They are included in international codes, Chinese code to ASC 716. Now there is a new ASC pre-standard for design. So there is an abundance of research. Thousands and thousands of pages that were printed on fluid viscous dampers since the 1990s. They are very well understood. They are proven in 700 structures around the world. And they are not dependent on frequency and temperature. Not dependent, obviously the damped frequency of a building is related to the undamped frequency through damping, but the difference is minuscule. The most important benefit is that they are they behave out of phase. As you have seen before, the force is related to velocity, which is a derivative of deformation, which means that the generation of force in the damper is out of phase with the deformation. That means the force in the damper is generated when there are no other dynamic buildings, dynamic loads on the structure, which makes this a very important thing because the force generated by the damper is not added to the other loads. They don't increase stiffness, and they don't have, and they are very, very, very reliable, as we discussed before. The last thing I want to draw attention to is the reliability in damping assumptions. This is another important aspect of fluid viscous dampers. You see here a graph which was taken by a paper written by Smith and Wilford, two Arab engineers, and it collates data, damping data from many, many researchers. There is definitely a trend of a reduction in damping with building height, but if you look at the distribution of the data, there are discrepancies. You can see measured data for a same height and type of building that differ, and you can see how the design assumptions, which are denoted by this black triangle, differ from the actual measurement. What does this mean? Let's see. This is just a small comparison. Let's say we have a structure which has no dampers and it relies on inherent damping. And we assume the inherent damping on 1.5%. And the actual damping is 0.75%. That means that the dynamic response on that structure will be 42% higher than predicted. The same structure, if let's say we fit dampers to it, we assume an inherent damping of 1.5, we have an actual of 0.75, and we add supplementary damping of 5%, which is actually measured and verified 5%. The difference in response will be only 11%. So this is a very important point to note, that by adding defined, measured sources of damping, we improve the reliability in this regard, because inherent damping assumptions are always suspect, because the good quality damping data are not very abundant. Now we go and discuss modeling, analysis, and property estimation. Just a brief on the analysis process, just to show that there isn't really anything much to worry about. We've defined our 3D form of the building, we select our force resistance system, preliminary analysis, and now we have to define what is damping and period and suitable analysis method. Then we will do a preliminary design of the damping system. We'll update the building model, analyze, design, and check the response acceptability. We'll see these things in detail now. A little bit more drilling down. The estimation of damper properties is you will see it in a little bit more detail very soon. It's a very straightforward process. Basically, it involves doing a straightforward modal analysis and using a spreadsheet for post-processing. Now, how to incorporate dampers in the model and analyze, we will see that there are, I mean, if we are using a linear or static method, which we have to account for damping implicitly and then verify it using basically an impulse load and using logarithmic decrement method. Or we can use time history analysis, a method of which a method like FNA, fast nonlinear analysis, is very convenient and very suitable for fluid viscous dampers and very fast. And we can do the analysis and basically verification within the analysis itself. So the model will account for the dampers itself. Now, excuse the formulas. I'm just going to. I'll make very simple. There are many ways to estimate damping properties initially, but we will focus on one method called the modal strain energy method, which is described in ASC 7 as well. Basically, very simply, the damping is the ratio of the work, the energy done by the dampers divided by 4 pi times the sum of the elastic energy of the building. This is, I mean, so basically what we have to do is set our target damping and calculate the energy basically consumed by the, and dissipated by the dampers and divided by the elastic energy of the building. We'll see very soon how this is done in detail. In this case, you will see you have these dampers placed diagonally. You have an interstory drift. So the energy of the damper is basically damping constant time times the period times the interstory drift cosine of the angle squared, which basically is derived from this bottom relation, which is the basic one. The energy of a damper within a cycle is pi times damping constant times this angular frequency times the deformation squared. So how do we do that? How do we calculate building energy and potential energy? Before I go into this, I want to make a disclaimer. What I'm describing here is going to be done by the supplier, by Taylor Devices. I'm just showing you that it's something very easy. It's easier than many things you do on a day-by-day basis, and it can be done in an engineering office without any hassle. So first, how do we calculate the building strain energy? Okay, to the left in brown is the ETAPS data, and we have the modal displacement, which then we scale using the target drift divided by the maximum modal drift here. Target drift can be anything. It's your target. It can be the target. It can be the drift that is the limit prescribed by the code, H/500. Or it can be the drift created by your ULS force system. Then this is going to be scaled appropriately, and we are going to end up calculating the kinetic energy. We are going to calculate the floor velocity by doing very simple, taking the drift and dividing by the period times 2 pi, and then we calculate the kinetic energy of the floor, and the sum of that is the total kinetic energy of the structure, which we sum up here. In a similar manner, we do the same for the energy of the dampers. These are the ETAPS data. They are scaled. This is our the stroke of the damper. This is the velocity is basically the angular frequency times the stroke, force, and then using the formula we showed before, we calculate the energy of the damper. And this is our damping here. And a strain energy of the building that of the dampers, which we calculate in this spreadsheet, divided by 4 pi times the strain energy of the building, which we calculated before. This is a typical method of how to obtain, and this we use this the damping to calculate the damping coefficient by basically using a simple iteration with goal-seek on Excel. So how do we model? The basic model for dampers is using the Maxwell-Viscous link. This top is the physical structure. In the bottom is the model, which we see here that we have basically what is denoted here is the link element. And we have to basically input the damping coefficient, the exponent, the stiffness, which is basically something that is provided by the manufacturer, the of the fluid column. And basically this is what we input in the model. I mean, this is a screenshot from ETABS. This is the first shot. I mean, we select here damper exponential. We restrain the axial, I mean, it's an axial element. And then we go to the second screen. And we see here that we can input the stiffness, which will be provided. It's not static stiffness. It's basically, it represents the flexibility of the fluid column, the damping coefficient, and the damping exponent. We could also use the effective properties if we are doing a response spectrum analysis or a linear modal analysis. We can use the effective properties. In this case, the stiffness will be 0, and the effective damping will be the effective damping coefficient that we have used. But this is not, I mean, if we have cases where we have a cross-coupling of modes, it wouldn't be recommended, I mean, to do that. But this is how we use implicit dampers without modeling the dampers in the model. So a few words about the possible analysis methods. As you can see, all of the methods can be used, but some of them we use damping implicitly by basically estimating how many dampers we need to provide a certain damping ratio to the structure, which we have seen how to do before, and using this number in our analysis. I mean, if we are doing a response spectrum analysis, we are going to reduce our spectrum using that number. Or if we are doing a static analysis for wind, we are going to use forces, as we will see later, that correspond to that damping level. To use the dampers actually modeled in the, however, in the building, we have to use either direct integration or nonlinear modal, which is the FNA method, which both account explicitly for the behavior of the damper. Even if we use static methods, we still need to verify the damping in the structure. And this can be done by basically, again, we have to use a nonlinear modal analysis by using an impulse load on the structure, for example, if we are interested only in the first mode. The FNA method is very, very fast. I mean, it compares in speed with static analysis. Response spectrum methods can be used, but with limitations. I mean, there are limitations as to which the code prescribes if we are not doing a performance-based design, which we have to observe. Now, for wind applications, I mean, if we are using a static analysis, a very important aspect is how to use the damping variance curves. When we do a wind tunnel test, we use high frequency force balance testing to generate, then there is a desk study and we generate the so-called variance curves. These damping curves allow for us to tune the properties of the structure and to extract the actual static loads that we need to design for. If you see here, this is a typical graph which shows oscillation versus overturning moment. And we see that I mean, as the period increases, the moment increases as well up to a plateau. And this is a better example. We have this blue line is our ISO criteria for acceleration. And we see that in order if we are having a structure with a low damping and damped, or I mean 0.5%, we have to go below a period of 7%, i.e. increased stiffness, or we can use damping at 5%, we are well below our acceleration limits. This is another damping variance curve, which shows basically, this is for a given, once we have decided our frequency and what the structure, what the period will be, this is generated to show us how the structure behaves with damping. We see that this differential here with denoted as A is the overall response in wind response, in moment in this case, from 2% damping to 5% damping, which is shown here. The dynamic content of the overall response at 5% damping is shown here. And it's this amount here. And the static response, we see that the curve flattens as we go to higher damping, which indicates that the response is static. The static response is this one. So now we know that we have to design the structure for the sum of the remaining dynamic response and the static response, and the damping system for the remaining dynamic response. So to recap, how to analyze, I mean, we determine our inputs, which could be ground motion, wind tunnel time histories, or static forces. Generate a structural model. We do preliminary selection of dampers, damper coefficients, and sizes generally. Initial sizing. We do the analysis as usual. You see here it's a comparison of two small frames. By adding dampers, we are actually reducing the demand capacity ratios, and we can utilize smaller members. And this is a comparative response. See how, I mean, how less stressed and how the damp structure is. This is a comparison between the two frames on the storing displacements. Again, you see the large difference. Relative storing velocity, same comparison. This is the comparison of interstory drifts. And these are the demand capacity ratios. Same thing, same forces. You just see that you can reduce the strength, demand, and the acceleration and drift by just adding a little bit of damping. And then we do an iteration to finalize our selection. These two plots are energy balance plots which can be produced in a software like GitHub's after a nonlinear modal analysis, the FMA. The top one is the undamped structure, and you see that there is a huge amount of hysteretic response damage, nonlinear viscous damping, kinetic energy, and potential energy. And in the bottom, you see most of it goes into nonlinear viscous damping provided by the dampers. A few words about the code provisions. Dampers are referenced in ASC 710 and 716, chapter 18. And they are referenced for testing and for earthquake applications. To use now for, so they are very well codified, not only in ASC, in many national codes, such as the New Zealand code, Canadian code, Chinese code, and so on and so forth. To use, to take full advantage of fluid viscous dampers, obviously, we have to use performance-based design, which can be done both for seismic and wind. If we are going to, if we are dealing with wind-dominant applications, we can use chapter 31, which is the wind tunnel, the chapter that deals with wind tunnel reduction, which allows reduction of the response under certain circumstances by 50%. And we use chapter 1.3, clause 1.313, which basically describes performance-based procedures. So performance-based procedures are allowed under ASC 716 and have been used in buildings. Some of them we'll see later. So for performance-based design procedures, for seismic, we have FEMA P58 and many other local codes in the US, like the PIER in California and so on and so forth. And there is a new ASC pre-standard for performance-based design for wind, which references dampers specifically. And it's a very useful document. This is going to be basically form the basis for replacing 716 in 2022. A few words about damper specifications. Specifications consist of two things. We have to define the damper, the parameters of the damper, and we have to define testing and acceptance specifications. The parameters we have to define is the damping constant C, exponent A, the force output, which is given by these two things, and the stroke, how long, how the damper, what is the movement, the longitudinal movement of the damper that we prescribe. ASC chapter 18 contains very comprehensive provisions on testing and specification, both for wind and earthquake. And wind testing should be relatable to the amplitude of wind that we will be experiencing. I mean, the amplitude of the movement that we'll be experiencing in the specific wind forces that we are designing. Also, since we are talking about very long design life requirements, there should be experimental proof and proof by calculation of the design life. So basically, in specification, we address energy dissipation, fatigue, and power generation through hysteresis and force velocity tests. For example, here you see on the left a typical force velocity stroke test, which has to be conducted on prototypes. And on the right, we have the damping force envelope, which verifies that the damper operates in terms of damping output and velocity as prescribed. And this is a typical hysteresis curve, which shows the energy consumption within of the damper. It's a force-stroke displacement relationship, and the area here is the energy after one cycle. Like we said before, the parameters, the exponent 0.2 to 0.7, good for seismic. 0.7 to 1 actually is applicable to wind. At exponents around 2, we are talking about lock-up devices in bridges. And here on the right here, you see the lower the exponent is, the more efficient, the fatter the loop is, so more energy is dissipated in one cycle. But then you reach points of diminishing return. You don't get any additional benefit. So when fatigue and power generation are not an issue, an optimal exponent for seismic is around 0.3. This is a typical report that will be given by tailored devices, which describes the characteristics of the damper, force output, and this is the force velocity curve. And this is a typical, this is a range of sizes, just to give you an idea about what sizes we are talking about. A typical damper, 2,000 kilonewtons, which can be used in wind applications here, will be like something like 2 meters long, 1.5 meters long. and about half a ton heavy. Some examples. This is a 181 Fremont Street, San Francisco, California. It's a 54-story mega brace system, 32 dampers, each one outputting 2,000 kilonewtons. It added 8% to the damping of the building. And basically, this is a design that was optimized for wind, but benefited earthquake also. And the saving on that compared to a standard, non-damp design was about 3,000 tons of structural steel, about 25% of the total. This was a design, resilience-based design, which went beyond performance-based design. I mean, they calculated downtimes during earthquake and all sorts of very esoteric things. It's, like I said, it's optimized for wind performance, but the damping ensures that the building remains elastic under the 475-year earthquake. You see here on the left is the lateral system of the building. The yellow, these are the consist of mega braces, mega columns, and inverted chevron trusses here. The mega braces traverse about 20 floors. And to the right is a schematic of a typical mega brace. On top you have the viscous dampers, which stroke about 6 inches. Secondary brace, primary brace, which is like a box plate structure. I mean, it has a thickness of 2 inches, I think. And these are BRB fuses, which are placed there to protect the assembly from the maximum credible earthquake with a minimum return period of 2,475 years. This is one project in which we used the force limiting damper because we had a combination of earthquake and wind. The damper was bilinear. Up to a certain velocity, it behaved with a high exponent, and then after a certain velocity, the pressure, we used a pressure valve system which opens up the damper and reduces the force output by lowering the exponent. This is a 40-story building, 250 West 55th. Here, 7 fluid dampers were installed in a damped outrigger configuration. There was it added 2% of damping, and they saved about $5 million, which was 10% of the structural steel. This is a schematic of the configuration. I mean, the dampers were installed in the top mechanical floor, and it was basically designed with a steel brace core and a steel hat truss with the outriggers connecting to the perimeter frame. This is basically the static wind forces as back calculated from the wind tunnel test. As you see, are much lower than what were prescribed by the ASC code and the New York code, building code. And this is a frequency response function which was used in the analysis of this damping system in this building. And another case study is the San Diego Courthouse, 24 stories, special bottom frame, 106 fluid dampers. They added 11% supplemental damping, and the rated force was from 1,500 kilonewtons to 2,000 kilonewtons. Here we see some schematics, the plan view. And here to the left is the elevation view, which shows the configuration of diagonal dampers. Typical placement was about 4 dampers per floor, sometimes 6 dampers. Here we see the behavior. I mean, here on the interstory drift ratio, with inherent damping of 1.5%, we go to 0.3%, and then with 6% damping, we had 11% in this case, we go to our limits. And here, these are the results from 20-year return period wind. in the transverse direction. As you can see in the top floors, if you compare the 6% damping to the 1.5% damping, you have a reduction of, story force in the order of 35 to 45%. This is a concluding slide. It's not the concluding slide, but it's just to put everything together. What I've described to you is not a new thing. Since 1990, Taylor Devices has installed 26,000 dampers in 25 countries on 700 structures. Some of these structures are very, very prominent, and you see them on your right. I want to stand on a specific one, which is the Millennium Bridge in London. I'm standing on it for two reasons: because it's a famous case, and because we haven't talked about bridges. Basically, when this bridge was designed, there was a problem of acceleration because of lateral footfall. So the structure, this had to be fixed. There was excessive acceleration. And the solution that I believe it was Arup and Atkins came up with was to install fluid viscous dampers, which basically reduced the acceleration from 0.25 G, I believe, to 0.06 G. As you can see, there are many prominent buildings incorporating this technology in the US, in China, in Taiwan, in Japan. Like I said, there are 700 structures in 25 countries. With respect to, I just wanted to, in conclusion, to note that since we started, promoting this technology in this area, we have test drove it in two cases. I cannot say much. I will say that we used it in two projects with Viscous, and we also tested it on a project with Nor Consultants. And I'm sure you can talk to them, the gentlemen, Mr. Michael Paschalis and Mr. Thuc Bui, and they will tell you what they think about the technology. So in conclusion, it's a technology that grew from its military defense and aerospace roots, with all the strict, design processes that come with that and the investment that comes from that. And it found a home in civil engineering, and it has proven itself since 1990 approximately in our field. It's the only technology that can reduce stress and deflection at the same time, and it has many advantages while providing the thing that is the most efficient to use in order to create an economical structure, damping. Thank you. If you have any questions, we can go to questions now.
Thank you, Nikos. We have a few questions actually.
Yeah.
Obviously, you mentioned about in UAE, this technology you use any projects. Did you employ? Yeah. So
the technology was tested on projects. I cannot say much. One project was already in construction, and the other project also was about to start construction. So there wasn't much scope, and another project was a tender. The technology performed very well. I'm sorry, I'm bound by non-disclosure agreements. I have the permission of the gentleman to say this much. I cannot say anything more.
Okay. One question is, see, obviously when you use viscous dampers, it will reduce the stiffness of the building or outriggers. So how the damping will be beneficial? Another side, yeah, that's actually you covered, but anyway, just can you repeat that? Yeah.
Can I answer?
Yeah, please.
Yes, that's an excellent question. Actually, this is one of the problems of thinking about it. It's a little bit counterintuitive. Let's think about it this way. You have a structure with an outrigger with stiffness K. and it deforms to some point, which up to the limit. Then you release that structure and the stiffness becomes less. So it will exceed this limit. Now, I'm doing it sequentially to resolve this counterintuitiveness. Now we inject damping, we increase the damping. What is damping going to do? It's going to walk the structure back below the limit. Don't forget that the structure that has the outriggers installed already has a very low inherent damping. So basically, you make the structure less stiff, but you take the energy out that was going to be taken by the stiffness, you take it out through damping. This is how it works.
One more question from Mr. Vijay Singh. Do local municipalities accept 5% damping for towers wind tunnel study when using viscous damper? Do you have any local application municipality approval? Yeah, the same question.
We are talking about wind now, right?
Yeah, wind, yes.
Okay. What I can tell you is this. First of all, it has been used and it is allowed in other countries. That's what I've shown you in the presentation. With respect to local authorities here, I'm not in a position to know how a local authority will react to a proposal. I don't see any reason why an authority would reject such a proposal, since it is proven both, in terms in engineering wise and by experience, and it provides a more economical structure. In the end of the day, it provides it creates economy for the economy of the country. What I can tell you is that I have approached the authorities, and the authorities told me that we don't need to get to approve the system. We will judge and design on its merits when it's submitted. This is what the answer I received.
Okay. There's a big question actually. As per the municipality rules, the design wind base shear is not allowed to be less than 80% of wind base shear calculated using code values. In such cases, how does damper help? Even if it reduces wind base shear by 50%, we are restricted to use at least 80% of ASC 7 wind base shear value. Basically, it's authority question. Yeah.
May I respond?
Yeah, please.
My response will have two parts. The first part, even if we constrain ourselves to a code-based design, ASC 716, which is actually the municipality, I believe, follows 705. But anyway, what the code says, chapter 31, is that if you do a wind tunnel test and you have significant obstructions within the vicinity, and you don't do another wind tunnel test, removing all these significant obstructions, then you are allowed to reduce by up to 80%. This is correct. But if you do a wind tunnel test and you take account of the surrounding potential obstructions that could create shielding or augmentation of the response, then you are allowed to reduce it by 50%. I'll give you an example. Let's say you have a building and it rises above a group of similar height buildings. There is no neighboring building that distinguishes itself from the surrounding neighborhood. In that case, interpreting the ASC code correctly, you would be allowed to reduce by 50% with one wind tunnel test. Now, so this is part of my response. The second part is, like I said, now we have we are talking about performance, based design, which, it will remove all of these obstacles from
Understood.
engineers. Yeah.
Okay. Another question is about how does a smaller exponent alpha produce flatter hysteresis, although it increases the generated damping force?
Actually, it doesn't increase the. I mean, I'll show you something. Let me just go to. The definition of the hysteretic curve can be found. I mean, you can do the mathematics. I mean, if you see here, this is the equation of the curve. So basically, yeah, this is actually for the linear one. But the important thing I want to show you is something else. Yeah, that's the one. The smaller exponent reduces the force at higher amplitudes where they are of interest in earthquake. But actually, in this neighborhood of low amplitude movement, it actually increases the force in relation to the linear damping. So when you have non-linear exponents, you have to see where you are. To put it simply to you, I mean, when you have a linear damper, the damping is independent of amplitude. It doesn't matter what amplitude you have in the building, the damping will always be whatever percent, 5%, 7%. But non-linear damping depends on amplitude. So you're going to have different damping at lower amplitude, higher damping at, at higher amplitude. So according to where you are on the curve.
A question from Mr. Mahmoud Bilal.
Yes.
How does it dampers perform against fire? And sorry, one more question in the same thing. Does dampers have more compression capacity than tension?
More compression than tension?
Yeah.
Dampers don't have either compression or tension. The damper doesn't, whether how they behave or whether they can sustain. The damper, okay, the spring, okay, let me clarify on the spring.
Yeah.
The spring is not actually a static stiffness spring. It's a spring that takes care of, I mean, it accounts for the flexibility of the liquid column. And it's actually, basically, it's used in modeling is to basically account for the sudden, a little bit compressibility of the fluid. But in order to do that, you have to have viscous movement. So this does not contribute in the stiffness of the structure. I mean, when you add fluid viscous dampers in the structure, you don't add stiffness. You don't change the period.
Yeah. About fire, how does dampers perform against fire?
Sorry?
How does dampers perform against fire? Do you have any
fire
rating?
Yeah. That's a good question. Fluid viscous dampers are fire rated. Basically, they are fire rated for 1 hour under a direct flame of 1000 degrees Celsius. So
1000?
1000 Celsius, yes.
So you can have a better fire rating like 2 hours, 3 hours also. Maybe you need to have protection measures.
Probably, yes. Yeah.
Is performance-based design is mandatory for viscous dampers?
Excuse me again?
Is performance-based design is a mandatory for viscous dampers?
The short answer is no, but if you use performance-based design, you will get much more benefit. As the other gentleman pointed out, if you don't use performance-based design, and you don't, okay, let's take the case of seismic, okay? If you are using code prescriptions, ASC 716, you can only reduce your seismic base shear by only 25%, whatever you do.
Yeah, okay.
So, but if you do performance-based design, it will be much more than that.
Is tailored devices for blast resistant building design, say where the pressure is 200 bar and above, can it be used?
For blast resistant?
Yeah, where blast resistant building has got a higher pressures,
Yes.
200 bars and above.
Yeah, that's an excellent question, actually. In terms of the damper sustaining the pressure, the answer is yes. But I will point, there are studies that study fluid viscous dampers used in blast design situations. And you can get a benefit definitely from the vibration component that comes after the blast wave. But fluid viscous dampers, if the blast wave is critical, then fluid viscous dampers will not much benefit. If you are interested, there is an interesting analysis, an interesting paper on that. I can send it to the gentleman if he wants, or
yeah, I think okay, it's Mr. Hemant actually. What you can do, you can share your mail ID. I think you not share the mail ID. They can post more questions.
Let me share the mail ID now because it's
so that they can directly contact you for any further.
This is my mail ID.
That's good. I think majority questions are covered, and I'll ask one more last question. One of your slides you mentioned by using dampers, there's optimization of 57% materials reduction.
Yes.
Did you, I mean, any practical approach, or is based on the certain conditions?
No, I believe this is the one. Yeah. Basically, this is a case study actually that was done in Oxford University.
Yeah.
And it compares. Okay, these buildings, I can share the paper with you, I mean, immediately. This compares a building, that 8-story building in this case, that was designed once without fluid viscous dampers to a drift, a maximum drift of 0.5% at SLS, I believe, versus the same building designed for the same limit, but using fluid viscous dampers.
So it is.
Yeah, and basically the cost, the material cost of the damped building was 57% of the cost of the standard design.
Okay, I can say thank you very much. If any further questions, it can be directed to Mr. Nikos. And I think that's all for today. Thank you, Nikos. Thanks for all attendees. I think there is a survey which we did as a standard survey. We just to know how many of our non-members have attended. Mr. Abdullah, are you there?
Yes. Here.
Yeah. Can you on the survey?
Yeah, it will be rolled automatically after the session ends, so it will pop up.
Okay,
yeah.
Sure. Okay, sure. Yeah, it's, thank you for everybody. And
thank you all for your time.
Yeah, Mr. Abdullah, thank you very much for your organizing again. Always brain behind the seminar, technology behind this Zoom for us. Mr. Abdullah is our secretary for the region.
It's my pleasure. Thank you very much.
Thank you, Nikos. We'll have a photo. We'll have one photo.
Yeah. Okay. So should I stop sharing?
No, it's okay.
It's okay. Yeah. Thank you.
Thank you, guys. Thank you.
Have a good night.
Bye-bye. Okay.